Hello, curious minds. Welcome to another episode of Finale AI. It's that time of year again, Nobel Prize season. The Royal Swedish Academy of Sciences is handing out those shiny medals to the brightest minds on the planet. So let's dive into today's topic, the 2024 Nobel Prize in Physics. Spoiler alert, it's all about machine learning and artificial neural networks. Yes, we're about to connect physics and AI, so buckle up. This year's Nobel Prize in Physics goes to, drumroll, John Hopfield and Geoffrey Hinton. They're the rock stars behind some groundbreaking discoveries that made modern machine learning possible. Hopfield laid the foundation with his work on associative memory, and Hinton, well, he leveled it up with something called the Boltzmann machine. Sounds fancy, right? We'll break it down. First up, what's associative memory, and why is it a big deal? Okay, think about trying to remember a word. You might start thinking of other related words until, bam, you remember the one you're looking for. That's kind of how Hopfield's associative memory works. It stores patterns, like images or words, and can fill in the blanks even if the input is incomplete or noisy. It's like a puzzle solver, always hunting for the closest match in a sea of possibilities. Cool, right? Now here's where physics comes in. Hopfield's background in physics helped him imagine this process like something straight out of a physics textbook. An energy landscape. Imagine the network searching for the lowest value in this landscape, trying to find the best match to the input. It's like physics meets brainpower. Weird, but it works. Next, we've got Hinton and his Boltzmann machine. Hopfield laid the groundwork, but Hinton made it even more powerful. Instead of just storing information, the Boltzmann machine learns from examples. You show it a bunch of patterns, and it adjusts itself to make those patterns more likely to show up again. It's like teaching the network through repetition, except instead of yelling at it, you let it figure out what works on its own. Much more sophisticated. So why is this machine so special? Well, it doesn't just remember patterns. It can also generate new ones. It uses statistical physics, yep, we're back to physics, to calculate probabilities and figure out what's most likely to happen. In other words, it can take what it's learned and make something new from it. That's a big leap toward creative AI. Okay, so what does this all mean for machine learning today? Hopfield and Hinton's work paved the way for the deep learning models we see everywhere now. From recognizing faces in your photos to making Siri sound a little smarter, these neural networks are the building blocks. And all that cool stuff you hear about AI? Most of it started right here. Want some real-life examples? Sure thing. Deep learning is used in particle physics. Yep, we're talking about hunting down particles like the Higgs boson. It's also used to analyze gravitational waves, spot exoplanets, and even figure out the structure of proteins. It's like the Swiss Army knife of modern science. But it's not all rainbows and unicorns. There are challenges too. As much as AI is changing the world, it comes with some big questions. Bias in algorithms, job displacement, and potential misuse are all serious concerns. Developing AI responsibly is key, so we don't end up in a dystopian robot apocalypse. Nobody wants that. Looking ahead, what's next for this field? Researchers are always pushing to make these models faster, smarter, and fairer, from improving how neural networks handle data to applying them in fields like medicine and climate science. The future is bright. But hey, let's not forget to keep our eyes on the ethical side of things too. Scaling up these models has been game-changing. Back in the day, Hopfield was working with networks of just 30 nodes. Today we've got networks with trillions of parameters. That's like going from a paper airplane to a rocket ship. But with great power comes great responsibility. These models are energy hogs, and managing all that data isn't cheap. So what's the main difference between traditional software and machine learning? In traditional software, you give the computer explicit instructions, like following a recipe. But in machine learning, it's more like letting the computer figure out how to cook the dish by tasting it over and over again until it gets it right. That's why AI can tackle complex tasks like language translation or identifying cats in your Instagram feed, things that are way too fuzzy for regular code. Quick physics refresher. How does that energy landscape analogy help us understand neural networks? Picture the network as a ball rolling down a hill, trying to find the lowest point or the most stable state. Every point on the hill represents a possible configuration of the network, and the ball is searching for the lowest energy state. When it finds it, that's the pattern the network decides is the best match. Simple, right? Well, sort of. And that's a wrap on today's Nobel-worthy episode. But here it is, another spoiler for you. We're dedicating tomorrow's episode to the 2024 Nobel Prize in Chemistry. Because my boss and a colleague were the recipients, it is hard to describe how proud and honored I feel about their achievement. I hope you found it as mind-blowing as I did. Let's keep the conversation going. Drop your thoughts, questions, or comments below. As always, thanks for tuning in, and catch you next time.